Another speaker, another mandatory seminar, taking me away from the experiments I so desperately needed to finish in lab. On March 28th, 2024, at Baylor College of Medicine in Houston, Texas, I sat down for a keynote talk by Dr. Thomas Reardon, a neuroscientist and vice president of research and head of neural interfaces at Meta. Now, for the next hour or so, he continued to show us a prototype of a wristband that allowed users to click, swipe, and even type by just moving their fingers in space. I had never seen anything like it, and I thought it would be years before something like that ever came to market. 18 months later, on September 30th, 2025, Meta released smart glasses with the neural band. Welcome to MaPa BrainLab. I'm Mayuri Patel, and today we're exploring the neuroscience behind the Meta neural band. Now, when I first heard of Meta's recently launched glasses, I had no idea a neural band came with it. In fact, the glasses can operate on its own, but the neural band enhances the experience without the need for physical touch or voice input. That sounds impossible, but as the world of neuroscience and technology goes, we've entered an era where we're rapidly developing technologies that only seem possible in sci-fi movies. As these devices become available and enter our everyday lives, it's important that we learn how they work. And of course, when I heard of the neural band, I immediately went to check if that wristband I had learned about just a year and a half ago was the same one. And it was. Luckily, Reality Labs published their findings this past summer of that prototype. I knew I had to dig into this paper and share how they developed it. So, let's get into it. Now, when we think about how humans interact with computers, we often consider the devices that allow us to send signals to the computer. And you guys know what that's about. Usually it's through a keyboard, a computer mouse, or the touchscreen on our smartphones and tablets. Of course, there's advanced devices that use cameras and sensors, but those only work as long as there's nothing between the movement and the sensor. And when we think of medical advances, there's robotic arms or speech prosthesis, but the big limitations with those are that they are designed and customized for single individuals, which means the same robotic arm for one person probably won't work for someone else. And this usually comes down to our neural signals or the differences in our brain signals. Now, those of you who are gamers might have heard of EEG devices or electroencephalogram devices for gaming, which are headsets that detect electrical activity from the surface of your brain and translate that into commands in the game. That sounds pretty cool. Well, there's several of them out in the market, but there's challenges with those as well. EEG signals are usually very, very noisy, and they usually require significant focus. Okay, so what I'm really saying is that nothing really exists that's generic and can be used by the general population to interact with a computer directly without a clunky device. A challenge. And scientists never back away from challenges. Thomas Reardon and his team at Meta Reality Labs decided to focus on a different kind of electrical signal measured by an EMG or electromyogram. Okay, hold on, let's back up. I mentioned an EEG in those gaming devices. So what are they, and how is an EMG different? An EEG records electrical activity directly from a large population of neurons in the brain. EEGs work best at the surface of the brain, where the cortex exists, because neurons in this part of the brain are lined up and have synchronized activity, which gives us a large enough signal to detect. So an EEG signal sums up all the signals from these neurons firing together. An EMG, however, is measuring electrical activity of muscles. So, imagine you want to move your hand. That thought generates a signal in your motor cortex in your brain, represented by the firing or activation of a neuron. The motor cortex neurons travel down your spinal cord and connect to different motor neurons, which then send signals all the way to your hand and allow your muscles to contract. An EMG records the electrical signals produced by those muscle fibers as they contract. And the EMG they wanted to focus on was an sEMG, or surface EMG, meaning it's located on the surface of your body and isn't invasive. Now, there are current EMG systems, especially for prosthetics, but they aren't used widely. The available EMG data from participants or patients is usually limited, and there isn't large enough data to help generalize across the population. But what if they solved this problem and used deep learning techniques? And that's where the hypothesis for this study came in. The MaPa team decided to validate their hypothesis that an sEMG, using the right tools and a large sample size, could provide a computer input that could work across a general population. Great. What next? Well, they knew they wanted to use an sEMG, but which muscles would they collect data from? They thought about how humans interact with the world and a wireless device that would be easy to put on and take off. The wrist was the perfect choice. They constructed an sEMG recording device that could be worn on the wrist. It's lined with dry electrodes, which are special sensors that record the EMG from the muscle activity in the wrist. Now, remember I said that these signals are unique to each individual? But maybe if they recorded from hundreds of participants, AI could help by learning the patterns and build a dictionary of signals that are linked to specific gestures, handwriting, and movements. If this is done well, then they could develop a decoding model, which is basically an algorithm that could read an sEMG from anyone and know exactly what gesture it corresponds to. So, the first thing the team did was construct 4 different sizes of this device so anyone could wear it. Now, overall, this neural band is the result of years of EMG research across over 200,000 participants. But for the first part of this study, 162 participants were recruited to perform 3 different tasks to help build this decoding model. The 3 tasks were wrist control, discrete gesture detection, and handwriting. The participants wore the device on their dominant hand and had to complete these tasks on a laptop. All right, so what is wrist control? During this task, there was a dot on the screen and a dark gray box as the target, and the participant had to move the dot to the target by moving their wrist. For the discrete gesture detection, they performed 9 distinct gestures, some which included a finger pinch, a thumb tap, and a thumb swipe. Finally, in the handwriting task, the participants held their fingers together as if they were holding an imaginary pen or pencil and would write the words presented to them in space. Just with these initial tasks, the raw sEMG signals revealed patterns of activity during specific tasks. They were onto something. But the next big question was, even with over 100 participants and signals, how well does the sEMG decoding model generalize? Okay, so if you put the band on the same person on different days or slightly different positions, does the model still work? Nope. The EMG signals look different. Okay, what if you train the model on one person's EMG data? Can it correctly decode another person's gestures? Nope. This also didn't work. These variations were due to the sensor placement, the different anatomy across people, and muscle physiology differences. Essentially, the model couldn't easily tell whether a signal change meant a new gesture or it was just a different person or a different session. The only time it worked is if you trained the model on the same person over multiple sessions, the model would become better for that specific person. What this means is that you'd have to train models for every single user. And this makes sense. Each person's EMG patterns are unique. But for a consumer device, it's just not practical if you had to collect tons of data from your wrist to train the model and to get the neural band to work. So now what? This happens quite often in the lab. As is the case with many science experiments, the findings might reveal something unexpected, and researchers have to adapt or devise a new approach. Instead of building a new model for every individual, they began exploring whether it was possible to train a generic or pre-trained model, one that could recognize EMG patterns from anyone, even people it had never seen before. To do this, they collected more data, specifically from 4,000 up to 6,527 participants, and trained neural network decoding models on it. The neural network is an algorithm inspired by how neurons in the brain learn from experience. It makes a guess, checks if it's right, adjusts itself, and tries again over and over millions of times until it recognizes patterns. This then leads to a decoder that can map an EMG signal to a specific action. To peek inside the model, the researchers looked at how it represents different gestures. They found that as the EMG signal passes through the network, representations of gestures become clearer, while irrelevant details like which participant is wearing the band or exactly where it sits fade away. In other words, the model learns to focus on the movement itself and ignore distractions, which is what allows it to generalize across thousands of users. All of this is done offline at first. What that means is that researchers take some of the collected data to train the model, then give it a set of EMG signals it hasn't seen before from other participants to see how well it predicts the correct actions. This offline evaluation lets them refine and improve the model before testing it in real time, with actual participants controlling devices or performing tasks. But offline success doesn't guarantee the model will work perfectly in the real world. When a person actually wears the device, signals can shift slightly depending on how the band sits on the arm, muscle fatigue, or even small day-to-day changes in the body. These tiny differences can confuse the model, and suddenly, an action it predicted perfectly offline might be wrong in real time. That's why online, real-time testing is the true proving ground. It's where researchers see if the model can handle the messy, unpredictable signals of everyday muscle movement and still perform reliably. For example, imagine a participant trying to write the letter A in the air. The model has seen thousands of examples offline, but in real time, the person's arm might move a tiny bit differently than in the training data. The decoder has to interpret the signal instantly, guessing the intended letter correctly despite these small variations. It's this moment, the model predicting intentions in the messy live world, that shows whether the technology is truly ready. So, they took 17 to 24 participants who had never done the three main tasks I mentioned previously. Using this pre-trained model, for the wrist detection task, the cursor moved correctly over 80% of the time. For discrete gestures, all of the participants completed the task by swiping, thumb tapping, or pinching and holding. And finally, for the handwriting task, participants on average wrote 25 words per minute. Now, when you're using your phone keyboard for typing, you can type around 36 words per minute. So while it was lower, it still showed that it was possible. Their pre-trained model was working. But what if you wanted to make it better? They found that just 20 minutes of personalization to the user's sEMG signals would result in about a 16% improvement in performance. Personalization works especially well for people who struggled most with the generic model. It's like giving the system a small tuning session so it can fit your movements perfectly. All right, that's a lot. Let's recap. sEMG signals are signals from muscle contractions. They're messy and totally unique. A model trained on one person? It won't work for someone else. What about training a separate model for every user? Nope, it's just not practical. The new approach, a generic model trained on thousands of people. It learns to focus on the gestures themselves, tuning out irrelevant stuff like exactly where the band sits. And in real life, people could move a cursor, do swipes and pinches, even write letters in the air. And here's the cool part. A little personalization makes it even sharper. Just 20 minutes of your own data can boost accuracy by 16%, basically fine-tuning the system to our own movements. These experiments showed that this wearable sEMG device is scalable, it's smart, and it's surprisingly precise, turning your muscle signals into real-world control. Okay, let's review some of the technical details before we wrap up. The actual sEMG recording device is a dry electrode multi-channel recording device with a high sample rate of 2 kilohertz. This was innovative since most EMGs require gels or invasive sensors and would work well for a consumer device. When they developed the band to visualize the electrodes relative to wrist anatomy, the team collected high-resolution anatomical MRI scans of participants' forearms. The device specifically extracts single putative MUAPs, or motor unit action potentials. If you want to dive deeper, the paper includes extra details on how the model works. Things like the specific features it extracts from the EMG signals, the network layers it uses to detect patterns and sequences, and the way it translates those signals into real-time actions. I won't get into all of that here, but if you want the full technical deep dive, you can check out the paper at www.mapabrain.com. All of this work, from decoding messy EMG signals to building a model that can generalize across thousands of people, became the foundation for the neural band. The team took what they learned from these early research prototypes and translated it into a sleek, real-world device you can actually wear. The neural band builds directly on this science, adapting to your unique muscle signals in real time, turning years of lab experiments into something you can use every day. These experiments show us that an idea and a vision, with trial and error, can lead to technology previously thought completely impossible. Now, how well it's going to work with the public and its general use over time is still yet to be seen. So, if you stumble on the neural band anytime soon, remember the science behind it, how it's collecting information from your muscle activity and translating that into real functions. You'd think it's magic, but it's really just neuroscience. And that's a wrap for the Meta Neural Band. If you're interested in digging deeper into the studies we mentioned, don't forget to check out the companion website, www.mapabrain.com, where you can find links to the paper and a glossary of terms. Don't forget to follow MaPa BrainLab so you never miss an episode. Science grows through dialogue and curiosity, so drop by the website and leave a comment. I'd love to hear what you learned about the neural band. And remember, the best way to learn science, especially neuroscience, is to teach someone else. So share your notes, invite a friend to join the lab, and we'll discover more neuroscience next time, here on MaPa BrainLab.